CLUMEQ is a consortium of 11 universities in the province of Quebec. CLUMEQ is also part of the national HPC platform, so we will be serving researchers across Canada, especially those researchers that have needs for a high-performance cluster like the one we have. In 2006, when we started designing this, the Van der Graaf accelerator, which was built in the 1960s, was still functional, but the university wanted to shut down this infrastructure. And I remember joking with my students, saying it would be very cool to put a computer in this silo. But of course, at that time, it was a crazy idea, and we kind of dismissed it. But later on, when we started drawing some concepts, we thought that to circumvent most of the classical problems that we find in conventional data center, we would need to build a round machine. And then this idea of a cylindrical machine came back.
CLUMEQ silo totally blows up the paradigm of data center design. The silo by itself is the crack. There's just no crack in there. It's just the whole facility cools itself. So the silo is built over 3 floors. You basically have a sub-basement where you have all the cooling infrastructure, and then you have 3 levels of compute racks. By doing this design in a round fashion and centering the switches on the 2nd level right in the center, it was the only way you can actually wire it up to 75 racks within 10 meters length. There's no way you could have done that in a linear fashion, more typical data center design layout. The silo is also incorporating free air cooling. For most of the year, you're actually able to drive the outside air in using 6 giant fans, able to blow 30,000 CFMs each. That's a total of 180,000 CFMs air handling capacity. That's massive. And there's a whole space on top of the data center that can be used as a thermal buffer. So if the entire chill water loop goes down, the rack can still blow the hot air. It's just being straight blown outside. So the machine can keep running as long as it has electricity, but without a cooling system. On top of temperature sensors and humidity sensors, it's also incorporating differential pressure sensors. You always want your systems to have just the right amount of air at any time during their operation. And the whole system is like a whole ecosystem that breathes naturally and adapts to the compute infrastructure demand and cooling. What's really cool about the free cooling story in this facility is the fact that in winter, the coils that are used in the summer to cool the system are actually run in reverse with the hot water loop of the campus. And that heat is being sent to the nearby science building, therefore driving a PUE even lower, making it one of the most eco-friendly facilities in the world.
Deploying such a machine is very complex, so you need to have experts. We chose Sun simply because they offered the highest performance cluster technology. Sun is a no-nonsense engineering-oriented company, and they have great HPC resources.
We had to design a machine that was not only very powerful, but also very well balanced. So on top of getting massive flops to be able to do computations, the interconnect between the nodes is also very powerful. We're talking about InfiniBand, QDR to each and every node in a full bisection via tree. And we were able to do the entire machine, that's 960 compute nodes in 4 minutes 56 seconds. And that really sets the pace and sets the target for the competition to go after. This is a one-of-a-kind system that will be able to run codes nobody else can run in Canada. And to some extent, it's already becoming the jewel of the crown of Compute Canada, and a whole lot of people are already lining up to be computing on this one.
The future is very complicated because of things like changing climate and changing habitats. So to deal with that complexity, we have to build computer simulation models that start to get quite large and require a lot of computing power. So having the extra power of the supercomputing facility is essential.
In a CFD lab like ours, we tackle different projects, all of them involving flow simulations. In most cases, though, we had to make the assumption of two-dimensionality for the flow field in order to be able to realize those simulations on our resources. With the CLUMEQ now, we intend to use the supercomputers to do three-dimensional simulations, and that should help us continue the development of this very promising technology.
What is the relation between Atlas and CLUMEQ? The CLUMEQ machine will be a kind of instrument in analogy to a microscope, which will help us to make models, solve the models, and compare it with the real experiments, and then we will say, yes, okay, we understand what happened during the Big Bang or shortly afterwards.
So far, we have worked very hard to implement this world-class infrastructure, but that's not the end of the project, it's only the beginning. The most important part of this project is developing expertise, and this is what we need to do for the future.